Good morning, and to my Polish friends, Cześć, and to my German friends, Guten Tag. I know it's at the end of season 3. We saw me trapped by a polar bear. Um, we left you on a cliffhanger, but don't worry, I was managed to escape that polar bear by throwing a cup of water on him. Because as we all know, polar dissolves polar. So in season 4, we're going to begin with equilibrium, a nail biter. Equilibrium will dominate chapters 13, 14, 15, and 16. Basically, the theory behind equilibrium, I can teach to you in 1 hour. And then the next 4 chapters are just variations on a theme. So without further ado, let's begin equilibrium. So any reaction in theory is reversible. So we just got done drawing an energy diagram that looks like, one of them looked like this, okay? And so this is potential energy. And on the bottom here, we call it the reaction coordinate. It's called the reaction coordinate because you can go, in chemistry and physics, you can go backwards and forwards in time. In other words, in theory, you can reverse any reaction, all right? You can think of the x-axis as time. You know, when you're, if it helps you, but in reality, we say it's a reaction coordinate. So suppose we have 2 reactants, A plus B, and they're going to react to become C plus D. Now, my equation would look like this. All right. Now, like I said, in theory, any reaction can be reversed, right? It's just a matter of how difficult is it to reverse that reaction. So you are used to us writing single arrows, okay? But from now on, we're going to be writing double arrows, meaning boop and boop, okay? 2 half arrows. What that means is, in theory, A and B can overcome their activation energy hill to become C and D. Likewise, C and D can go the opposite direction and go back and become A and B. The forward reaction has a smaller activation energy hill. The reverse reaction has a much bigger activation energy hill. And so that is why in this diagram, the forward reaction is favored. It is easier for A and B to get over their activation energy hill than it is for C and D to get over its. So in other words, we would say the forward reaction is favored, okay? Now, sometimes you may see in a textbook or in writing, they will change the length of the arrows to indicate which direction is favored. But not always. Now, if a forward reaction is really, really favored, sometimes they'll just put a single arrow, meaning that the reverse direction, that it just may be so difficult for these guys to get over their hill that for all intensive purposes, the reaction is forward, okay? So, like I said, to just summarize here, all reactions in theory are reversible. So we draw that as double lines. A and B can react to become C and D, and C and D can react to go back to become A and B. All right. So the next thing I'm going to show you is a little demonstration. Okay. So I'm going to take you back over to the all right. So I have two containers. Here's A and B, my reactants. Here's C and D, my products. Okay. Right now I have all reactant and 0 product. Okay. I have two containers. They are not of equal size. This one is much bigger than this one. This is going to represent the forward reaction. This one's going to represent the reverse reaction. So when we first start off, we have all reactant, no product. So there is no product to go back over the activation energy hill. Lots of reactants with. So as the reaction progresses, you can see that a little bit of the product is reacting and turning back into the reactants. But comparatively wise, there's still a lot more reactant becoming product and very little product becoming reactant. As we continue, where do you think the two levels are going to end? The two levels are going to be equal? Now let's just see, I've got these graduated. That's got about 400 mils in it, and this has 500 mils. Okay. We're going to keep going. All right, so now they're actually at about 450 each. So if I'm putting 450 mils in there and 450 mils in there, the levels aren't going to change anymore, right? So what we say has happened is we've achieved equilibrium. So no matter how much more I go, the water levels are not going to change, okay? Now I'm just going to get a Sharpie and I'm going to mark along there so that we can see the water levels. So as you can see, there is more product than there is reactants, okay? So what would happen if we started with all product and no reactant? I'm going to dump all my reactants. Okay. Now we're going to do the exact same thing. What do you think is going to happen? Okay. So although the forward reaction is favored, right? We have a bigger cup for the forward reaction. There is no reactant. So when we begin, there's almost nothing going the forward, everything's going reverse. But as we progress, you can see there's getting to be more and more reactants that can almost there. Let's see what we're at. Almost. You can see now that there's a lot of reactant. And yep, 450 and 450. So now it doesn't matter if I keep adding this, the levels are not going to change. And so you can see as soon as the water stops rippling that the levels are the same as they were when we started with all reactants. Okay, so we have reached equilibrium. Okay. Now we got one more demonstration for you. Suppose I add a catalyst and speed up the reaction. Now I can't, in this situation, I'm going to be the catalyst. All right. So if I speed up the reaction, I go faster. I don't spill too much. So adding a catalyst did not change the relative values. All it did was get you to equilibrium faster. So when you speed up a reaction with a catalyst, all it does is get you to equilibrium quicker. Okay? So if you get confused in equilibrium, think back to this exercise and that the equilibrium constant is a ratio of your products to your reactants, okay? And in this case, we always had more products than we did reactants. It didn't matter where you started. I know right now it looks kind of the same because I spilled a lot of water, but in the beginning you saw, because the forward reaction was favored, we will always end up with more products than reactants, and the ratios will always be the same. So let's do some math. So I'm going to switch over to Notability. And the first thing we're going to do is write the equilibrium expression. So suppose we had this reaction. So the equilibrium constant is a capital K. Oh, I didn't balance the reaction here. The equilibrium constant is a capital K. And then we do the products over reactants, and it's their concentration, products over reactants, okay? The brackets mean this is their concentration in molarity. And then we raise them to the power of their molar coefficient, okay? Now that is different than what we did with kinetics. So please don't confuse kinetics with equilibrium. With kinetics, we used lowercase k. Equilibrium, it's uppercase k. With kinetics, there are two things that affect the rate constant. And that was temperature and a catalyst. Whereas the equilibrium constant the only thing that affects the equilibrium constant is temperature. Okay. So let's now with this expression up here, brackets are in molarity. Now I wrote it like this. However, many times, oh boy, that's gas. There we go. Many times, gases technically don't have a molarity. Okay. When we're dealing with gases, we are more interested in their pressure. Okay, so we can write this expression in terms of pressure. Okay, so this is the equilibrium expression. Okay. But like I said, we would more likely do Kp, which is in pressures. So it would be the pressure of hydrogen, products over reactants, the pressure of water over the pressure of hydrogen over the pressure of oxygen, raised to their powers of their molar coefficients, okay? So if they give you pressures, you are actually calculating Kp. If they give you molarity, you are calculating K, okay? Now you can convert one to the other because with the ideal gas equation, PV equals nRT. And then P over RT is equal to N over V. What is N? N is moles. What is V? Volume. What is another name for moles per volume? So molarity. So molarity is proportional to the pressure over RT. So I could say that N over V is my concentration, and molarity is a measure of concentration. So I can relate then, so if I were to take my molarity of each of these, and substitute in, okay, substitute in substitute that in. So I could substitute all of that in with pressures instead of molarity. So if I did that, I could relate Kp to K with the following equation. Delta N is the change in moles from products to reactants. So, for example, in this reaction, I've got 2 moles of hydrogen, 1 mole of oxygen, and 2 moles of product. So in this case, I would have 2 moles of product minusing 3 moles of reactant. So my delta N would be -1, okay? So because all of my compounds in this reaction are gases, I would be more likely to be using Kp instead of K, okay? Now, one last thing to include about K, we do not include, and the same thing with Kp, we do not include liquids or solids in the equilibrium expression. So when I wrote this equation, I was very careful to make it water gas, okay, not water liquid. Because if I made it water liquid, products over reactants, again, I'm just pretending we've got molarities for these guys. Why wouldn't I include liquid water? Well, what is the concentration of a liquid or a solid? It's their density. And the density, more or less, is a constant. So if the concentration of a liquid or a solid is their density, and the density is a constant, why would I have two constants in an equation? I could just combine these two constants together, because a constant and a constant just gives me a constant. So if this was my reaction and I was dealing with liquid water, the equilibrium expression would be this. There'd be a 1 on the top. And this K would have consumed or subsumed that constant into it. Okay? And if we were doing KPs, it would be this. Okay? So let's do some example problems. Okay? And so this portion is the end of the theory portion. The next video will be on example problems. Okay? You guys have a wonderful day. Dobranoc, and see you tomorrow.